Hi, I'm Jim Rautio, President, CEO, and founder of Sonnet Software. I'm going to talk about current induced in silicon substrates by spiral inductors. This affects the Q of spiral inductors and is a big problem for spiral inductors on silicon. The first part of solving the problem is understanding the problem, and we're in for some surprises. It's well known that silicon RFIC inductors induce current in the nearby silicon substrate by magnetic induction. Are we sure? No problem. We can check it by visualization. We can look at the current in the substrate and make sure that our understanding is correct. For example, what direction does the current flow? When does it flow? What does a pattern ground plane actually do? We'll look at all these questions during this presentation. Popular wisdom says that silicon inductors, and inductors like a small magnet, right, induce current in substrates by magnetic induction. How else would a magnet, electromagnet, induce current, or an inductor induce current? It has to be by magnetic induction. These are also called eddy currents. Note that eddy is not a name. And also note that eddy currents are more properly used with a conductor that is moving through a magnetic field. It induces eddy currents. But eddy currents is a popular term for the substrate induced current. To our knowledge, substrate current visualization has never before been published. This is a very important part of spiral inductor loss on silicon. Why hasn't there been any research in it? That's a big puzzle. We visualize substrate currents using Sonnet by means of something we call sense metal, which we will describe next. Sense metal has no effect on the fields in the structure we're analyzing. This quote conductor is actually set to a surface impedance that's very high. If we make it an imaginary surface impedance, it can be analyzed slightly faster. So we'll make it imaginary reactive, 1 million ohms per square. Something with that much impedance is going to have no effect on electric fields or magnetic fields or anything. However, a very tiny current will be induced in the sense metal that is proportional to the tangential electric field. It's like a voltmeter. So we can visualize the tangential electric field on the surface of the silicon by using sense metal. But the tangential electric field on the silicon, on the surface of the silicon, actually anywhere in the silicon, is proportional to the tangential current density in the silicon, and it's proportional by Ohm's law, based on the conductivity of the silicon. So we can put in the sense metal and we will see a plot, and we can even calculate numbers of what the current is in the surface of the silicon. And here we see just such a plot. This is JXY, which is the magnitude, is the x-directed current squared plus the y-directed current squared, square rooted. So it's the magnitude of the current flowing tangential to the surface of the substrate. Z-directed current, current flowing perpendicular to the surface of the substrate, is not shown here. You can also see a ghost outline of the spiral inductor, so you can see where the spiral inductor is with respect to the induced current. And yes, of course, we see the current is flowing indeed in a loop, just as we would expect for a magnetically induced current, flowing in a loop round and round. A little bit of a problem. Why isn't it centered? We're using a symmetric excitation. Well, it's 1 volt on this line and 0 volts on this, so it's not quite symmetric. What's going on here? And also another problem, why is the current outside of the spiral inductor? It seems like a magnetic current, magnetically induced current, would be strongest where the B field is strongest. It would be inside the inductor. Very strange. But, well, at least we've got confirmation that the current is indeed flowing in a loop underneath the spiral inductor. If current's flowing in one direction on the spiral inductor, the induced current, by Lenz's law, should be flowing in the opposite direction on the nearby conductor, in this case, semiconducting silicon substrate. Let's check that a little bit more. I'm a little puzzled here. So let's just look at JX on the left, and we'll look at just JY on the right. So JX is flowing to the right, and we have maximum JX. Wait a minute. The current is flowing away, or 180 degrees later, towards radially. It's flowing radially from the spiral inductor. There's no JX up here. It's 0. Let's look at JY. Oh my goodness. JY is also flowing away from the spiral inductor. This is not expected, is it? I have talked to probably several hundred skilled RFIC designers, and asked them which way they thought the current was flowing in the spiral inductor, and everyone says it's flowing round and round. And this plot is not consistent with that understanding. If it's magnetically induced, it has to be flowing round and not flowing radially, but it's flowing radially. What's going on here? Well, let's look at it in a little more detail here. Sonnet itself does not do arrow plots. However, we have a very good API to MATLAB. It's called Sonnet Lab. And we can take any data that is inside Sonnet and put it into MATLAB and process it. And I use Sonnet Lab and MATLAB to take the data for the current distribution, and used a MATLAB utility called Quiver as in a quiver of arrows, to add the arrows to the plot. And here we go, and we see indeed the arrows at phase equals 0 degrees. This is 10 gigahertz. Phase equals 0 degrees. All current is flowing in. 180 degrees later, all the current will be flowing out. This is very strange. How could that possibly be? Notice the excitation is cosine omega t. So that, interesting. The electric field is maximum at cosine omega t. Let's see what happens as we go towards 90 degrees. There's 30 degrees. The current, induced current, is quite a bit reduced. 60 degrees. We'll look at this frame by frame here for a little bit. Then we'll do an animation. 60 degrees. Wow. Current's almost all gone. At 60 degrees. At 90 degrees, the current's coming back and in the opposite direction. Most interesting. But at all times, the current is radial. There is, if you look very closely, you can see a little bit of circular current as you go through the animation, but it is extremely minute. Circular current is induced by magnetic field, so how could radial current be induced? Well, perhaps electric field. Let's look at an animation here. There is one cycle. We're going through an entire 360 degrees. I'll go ahead and play that again a couple more times here. Going through an entire 360 degrees. We'll do it 2 more times. Right there. You see the current goes in and then goes out. Almost entirely radial current. One more time here. There's the current flowing radially. It is, of course, induced by the electric field, not the magnetic field. It is not magnetically induced current. Eddy currents, in any sense of the word, are induced by magnetic field. These are electrically induced currents. Magnetic induction has nothing to do with it, because if the conductor underneath the spiral inductor were, say, copper, with a conductivity about 1 million times higher than the silicon, we would have magnetically induced currents. electrically induced currents would be almost nothing. But this is not copper. This is not a good conductor. Silicon is, in fact, a semiconductor with a conductivity, in this case, 8 Siemens per meter, about 1 million times, almost 10 million times less than copper. Sometimes RFIC designers refer to the skin depth of the silicon. In this case, if you plug in into the equation for skin depth, the skin depth comes up as 1,000 microns, about a millimeter. If the condition for skin depth, if silicon is a good conductor, and if you plug in the equations for a good conductor, you'll find that you have to get into a frequency of several terahertz before you can even pretend that silicon is a good conductor for the concept of skin depth. At 10 gigahertz, 1,000 micron skin depth, the silicon is not skin depth is not the issue. Well, let's verify that. I mean, yeah, that's what the equations say. Let's go ahead and take this sense layer, and we can parameterize it in Sonnet. So all you have to do is type in a number, and it sinks the sense layer into the silicon. So here it is at the surface. You've already seen this plot, in this case without the arrows, but we know the current is radial. And now let's go down 20 microns into the silicon, and indeed the current is, this is plotted, all plotted at the same scale. The current is substantially reduced. So let's go down another 20 microns, 40 microns now. Current is almost completely gone in the silicon. The current is hugging the surface, but it's hugging the surface much closer than skin depth. It is hugging the surface because that is the closest way to get to ground, which in Sonnet is on the sides of the circuit. The perimeter of the circuit is where ground is on Sonnet, and it's hugging the surface. We'll go back 2 slides. It's hugging the surface so it can get to ground. And okay, your spiral inductor in your RFIC will not have a perfectly conducting grounding sidewall here. But what will it have? It will have additional circuitry there. The circuitry, the VCO or the LNA that you embed this inductor in, the circuitry of that, and maybe there's some digital control circuitry hanging around too. All of that will be hanging around out here right where the Sonnet sidewall is. And this substrate current will go to the closest ground, and if the potential of that circuitry, the external circuitry, resembles ground in any way, the electrons don't care that that's your precious circuitry. They will head right for it and cause all kinds of problems if you're not careful. So this current, we have to figure out where ground is, where that substrate current wants to go. Now, I said earlier, well, it's differential spiral inductor, right? But was it fed in a balanced fashion? No, it isn't. We have 50 ohms. The previous current distributions we showed were 50 ohms on ports 1 and 2. However, the 1 volt source is applied only on one side. It's not applied on both sides. So while the spiral inductor is almost symmetric, it's not quite symmetric. We almost have a plane of symmetry right down the middle of the spiral inductor, and that makes almost a virtual ground. Wait a minute, the virtual ground would be volt potential is halfway between these two. The virtual ground will be at half volt potential. The sidewall over here is at 0 potential, so the sidewall is much more attractive for the current to flow to, the substrate current to flow to. If we change the excitation so that it's balanced, half a volt on either side, resistance doesn't make any difference here for the current plots. Put half a volt on each side so we have a balanced excitation and an almost symmetric spiral inductor. Guess what happens to the current? And note the plots are plotted at the same scale. And we have 1 volt source in both cases. And again, resistance here does not change the current plot. Notice that the current now all goes to the center, and if you do an arrow plot, you'll see it all goes to the center with the ground plane. we have a plane of symmetry. Almost, it's not quite symmetrical here, it's not quite symmetrical here. But other than that, we have an almost virtual ground going right down through the center, and the substrate currents much prefer to go to that nice close virtual ground rather than going out to the Sonnet conducting sidewalls, or certainly we don't want it going out to your circuitry, the rest of the circuitry of your circuit that will be out here someplace just waiting to receive to be affected by any of the electrically induced substrate currents. So whenever possible, make the excitation, when you use a spiral inductor in your circuit, make the excitation symmetric as well as a spiral inductor, and you will see less crosstalk due to induced substrate currents. Now, what happens under a pattern ground plane? Here we have a pattern ground plane under that spiral inductor. These the strips in the pattern ground plane are 1/2 micron wide with 1/2 micron gaps. And look at the current underneath these, and you see, well, it looks like about one stripe per current, one stripe per ground plane strip, or is it? Well, we'll check here in a second. And also, what direction is the current flowing? Well, intuition says the current should flow along the strips here and then sideways. Oh, wait a minute. You know, the spiral inductor, you can see the spiral inductor outline with the tiny white lines here. The spiral inductor was inducing current radially, so maybe this current's flowing radially. Well, if that's, well, what direction is that current flowing? Let's go ahead, and this current, it turns out, is flowing radially. It's leftover current from the electrically induced ground currents from the spiral inductor. And you can actually increase the Q of this spiral inductor by increasing the length of the pattern ground plane to cover that. The pattern ground plane provides a short circuit to the electrically induced ground current, which is why it increases the Q. It had the pattern ground plane, as long as the metal is thin, compared to skin depth, it has no effect on the magnetic field. It affects only the electric field. So let's take a close-up of those stripes, and guess what? There is one finger, 1/2 micron wide, and there are two stripes per finger. The stripes are on the edges of the fingers, and if you look at the current direction is horizontal here. It goes perpendicular to the stripes, and there's also z-directed current, which is not shown. This is amazing, isn't it? The substrate currents just are not doing what we expect. They are almost always doing flowing 90 degrees to what one would expect here. Another thing also, the currents in each stripe are flowing in opposite directions. If this stripe of current in the substrate is flowing from left to right, this one is flowing from right to left. And 180 degrees later, they will both be reversed. They're always flowing in the opposite direction. The effective finger width, we did what I showed earlier was a 1/2 micron finger width. The title slide had a 2 micron finger width. We also did 1 micron finger width. No ground shield. The effective finger width is very small here, but the finer the finger width, the better the result. The 1 micron and 1/2 micron are almost identical, which means in Sonnet we can do something called anisotropic metal, which allows current to flow in only one direction. And you just, as finger width gets finer and finer and finer, 1/2 micron, 1/10 micron and down, it's really hard for any EM analysis to model to actually EM analyze the entire pattern ground plane. So what you can do with Sonnet is just leave the cell size fairly large and just put down solid anisotropic metal, because the finger width does not matter. You put in solid anisotropic metal and you get essentially the same result. A very fast way of analyzing extremely fine pattern ground planes. In conclusion, current is not magnetically induced in a silicon substrate. directly contrary to what I and all the RFIC designers I talked to, every one of them, thought. It is electrically induced. Big surprise here. This is a major point for RFIC spiral inductor design. Q is the holy grail that we've got to increase to get working circuits, and everyone is thinking it's magnetically induced current flowing circularly underneath the spiral inductor. It is electrically induced current flowing at right angles, and that's why a patterned ground shield works. It shorts out the electric field that would otherwise induce current in the substrate. The pattern ground shield has nothing to do with the magnetic field in increasing Q. Understanding substrate current is a brand new research field. As far as I know, no one has researched this, no one has published in it, and there's still a lot of research opportunity here. Thank you for your kind attention.